Good morning to all of you. I think it is time to start today's lecture, which will be given by Samriddhi Shankar Roy, who works here at ICTS. So, Samriddhi.
Let me begin by thanking all the organizers, in particular Bulbul, Chandan, Srikanth, who are here, Pinaki, Madan, Vijay, etc. So this is a long list. So the areas that I work on are in areas of turbulent transport and turbulent singularities, etc. I'll try to see if I can make some reasonable connection between entropy, information, and order in soft matter. At least I hope to a first approximation there'll be some information that I'll be able to convey. The other thing, of course, as you can see from the title, this is rather generic. Since, as far as I can tell, except my students here, the rest of you are not from the turbulence community. So what I will try to avoid is, messy details that we worry about. But I try to, I'm around, as Chandan said, I work here. So if someone's interested, I'm happy to provide them. But it's already it's already messy. So there's a reason why I'm doing this, because Professor Rama Govindarajan did talk about the spherical particle approximation and some of the work that's being done in our extended group. So I thought that maybe it's a good idea to sort of tell you what's going on in our community, and hopefully some of this will be interesting for at least some of you. So I'm essentially going to talk about, visually illustrated here, these two phenomena in this talk, and I'll explain what this phenomenon is. Let me begin, by just having a physical picture in mind of what's the setting that we are roughly looking at. So there's a whole bunch of things here where you do see the role of both, and I'll come to this in a bit, where you do see the turbulent transport of small particles, all right? We'll relax that small part in the particles in a bit. Rama mainly sort of in her lecture focused on the microphysics of cloud, which is something that many of us are interested in. But then, it goes all the way up to various scales, and there are potentially various settings where a lot of these ideas can be carried forth. What I'll try to do is more a general principle of what works, what doesn't work. And again, this is sort of just to, even if we forget everything else. So the reason why this technical side comes so early is just to tell you that the usual strategy that people like us adopt is that we look at the fluid, the turbulent flow, as a solution of the Navier-Stokes equation in the limit of very small viscosity or very large Reynolds number. Unlike engineers or people working with more realistic systems, we avoid boundaries. And in most cases, unless I sort of specify, we will be working in the space of periodic functions, which is the setting that typically we look at. So these are the set of equations that Rama would have shown you in a talk, which is for spherical particles. So if x and v constitute the phase space in which the dynamics is evolving, then you have these coupled equations where x dot is v, and then you have what's known as the linear Stokes drag model, or or a simplified version of the Maxey-Riley equation, and you have a rather simple equation to get around actually studying the dynamics of these spherical particles. Computationally, it's a challenge, but I'll talk about that. Yes, actually, what's not even clear now, there's some recent works by Titi and others, which has to do with whether, for atmospheric turbulence, because of the boundary layer, whether even the three-dimensional notion is. But incompressibility is a better approximation. Essentially, what's happened is now with certain measurements in the atmosphere, it's not very clear whether the energy, for example, the energy distribution or the energy flux, whether it's a quasi-2D system or really a 3D system. It sounds a bit strange, but there is some debate about that. G is gravity, but I will not speak at all about this this is just to refresh people, any of you who were there for Rama's talk, just to give a place for me to start, essentially. For non-spherical equations, and in each case I will comment on the equations of motion. Typically, the equations are more complicated, if you like, because of added degrees of freedom, and we'll see how to take care of that. So the caveat, which is global for my talk, and also for the kind of work that goes on in people from our community who are working with clouds, is that we are essentially dealing with dilute suspensions. So one can get away with ignoring certain particle-particle interactions, if you like. A more serious one, when particles become large, is the fact that this is a one-way fluid coupling. So the fluid acts on the particles, but the particles don't do anything to the fluid. So typically, if you're really small particles, and hopefully I'll show you some data from experiments and theory and simulations. Hopefully, if the particles are really small, this is an approximation which is all right. Okay. And again, as I mentioned, we'll be in the regime of what's known as statistically steady homogeneous isotropic turbulence. That's the simplest to work in for no good reason but that. So, of course, the natural question that one can ask is, why aren't we looking at random flows? We could just as well study this problem of fluid particles in a random flow, in a smooth flow. You can build up a kinetic model of a flow where you can impose your favorite scaling. So, different people have different answers to this question, apart from the fact that in nature, in the systems that we are looking at, flows are typically turbulent. But I should add that turbulent flows are essentially different from flows that you can build up, let's say, through an Ornstein-Uhlenbeck process or a Brownian-Wiener process, etc. And they're essentially characterized by these three ingredients. And if time permits, later I will comment where these ingredients actually matter. One is the fact that they're, of course, chaotic. That's easy to build. The second is that they're irreversible. And what's most crucial is the fact that they're intermittent. So what I mean by that, maybe I can just show this as an example, just to fix ideas. Okay, this has nothing to do with the rest of the talk, but because it's a non-turbulent audience, just if certain things, features of turbulence are of you carry back, this is good for me. Is, for example, if you look at the PDF of fluid acceleration, you see these very long tails. I mean, you can't read it, but on the y-axis is the acceleration normalized by its typical RMS values, and you see these extreme events, and so you have finite probability of accelerations which are at least 50, 60, 100 times their RMS speed. And this is a paper by Bodenschad's group. These are experimental measurements, and it does seem weird that you have these really strong extreme events which govern turbulence. And this you see, for example, this is a particle trajectory, the kind of picture that we've seen a lot, for example, in Srikanth Chandan's talk, is where you color code and you just watch the track of a single particle, a tracer, if you like, and the different colors represent different speeds. So even in a small window, let's say the particle is released here and it's going around vortices, presumably, you do see that it speeds up enormously. All right? All of this makes turbulence itself a slightly messy, a slightly weird system to work with. And essentially, these extreme fluctuations, and that you also see, this is a snapshot of the vorticity field, that you essentially see everywhere, and this is what people in the trade call an intermittent behavior, and it's something whose origin we still don't understand actually in turbulence. And all of this, I mean, this is again a matter of, slightly a matter of opinion, but all of this presumably is connected with the structure in physical space of a turbulent flow. So essentially, if you go into a very high Reynolds number flow, you will see proliferation of vortical structures, and typically, typically they look like these subway wraps. So you essentially have a core which is strongly vortical, and they're surrounded by a very straining, a strongly straining region. So there are these extreme interfaces where, let's say, the gradient, the velocity gradient tensor, the symmetric and the antisymmetric part, have very strong amplitudes, but they're just sitting next to each other. So there's nothing sort of benign about this. So if for the rest of the talk, since I won't mention much about turbulence, so the only sort of picture that I would like all of you to keep in mind, especially students, if this is your first turbulence talk, is that I will be feeding particles, which I'll describe a little more, in flows which have these strange structures. So there are sort of, and which are spatiotemporally changing. So you might have a strong vertical filament here, and in a short time that may have disappeared and sort of popped up elsewhere. So just as a quick as a quick sort of remark on all of this is, if any of you are interested. So recently there's been this strange thing called decimated turbulence, where some of us have been involved in, which sort of tries to throw new light into why all these structures are why turbulence is what it is. Okay, so that's sort of a crash course in, on the flow that we are dealing with. So now it's time to talk about particles. So again, I will take off where Rama left off, and also where Stefan Herminghauser's talk last week. And I'll talk about what sort of particles we have in mind. So you can think about small water droplets in air. You can think about bubbles in water. Or you can think about a blob of ink in water, all right? And essentially, if you have a certain fluid density, a certain particle density, everything, a lot of the dynamics is controlled by what the density ratio written in the strange form because of other reasons, what this density ratio really is doing, okay? So what's special about these particles? So this is a sort of, so I'm still on the spherical limit, okay? So what these particles are doing is the following. So on the left-hand side, this is really because of the nature of this meeting right now. So on the left-hand side, what we have essentially is a potential energy landscape, which is artificially created through a combination of sines and cosines, but which are spatiotemporally moving. And you put in a bunch of particles with exactly the sort of equation that Rama discussed, and you allow them to have a hard sphere repulsion, right? So they hit each other and they bounce off. Now, given that this is, sorry, the sort of, the movie degrades very fast, but it'll recover. So what you see is that you have these spatiotemporally localized structures. Now I'm not going to talk about this, but this is just to whet your appetite. And then when you actually go and analyze these structures, they turn out to be very similar to a crystalline structure. So you can do your usual GFR, etc., and you end up forming these sort of quasi-stable hexagonal structures at the minima of these potentials. But because the dynamics is dissipative of the particle, if you remember the equation, this is happening for purely elastic collisions. There is no dissipation at the collision, but just the fact that there is an underlying flow which is making it sample strange things. On the right, and that's Mohit did this, who's sitting here. On the right is actually a turbulent flow, two-dimensional turbulent flow, the standard sort of picture that one sees. And Mohit sort of put in a bunch of particles which have soft sphere repulsion. So it is a 1 minus the standard R over sigma squared potential. And you see that these sort of slightly penetrating particles seem to do different stuff from the ones which are being shown here. The reason why I'm showing this is not to... no, this is a solution of 2D Navier-Stokes. And this is just to see if I can have at least one picture which is which is easily understandable to Chandan, Srikanth, and you, etc. Which is, yeah. Exactly. The particle relaxation. That's right. But however, what I will not talk about is that we can define a certain Kubo number, which is the ratio of this time scale, and the dynamics is completely determined by this Kubo number. So for certain range of this non-dimensional parameter of the landscape, the correlation time scale of the landscape, and the particle relaxation, you do have crystalline order, and in some cases, if you look at, let's say, G of R, you just see a fluid ice behavior, right? So the point of this is just, it illustrates the fact, sorry. No, just a potential. So the fluid, so in the Maxi-Riley equation, U, the fluid velocity that one puts in there, is just taken to be the gradient of some potential. And yeah, that's on the left-hand side. And the right-hand side is a solution of 2D Navier-Stokes for high Reynolds number. Right? I mean, basically we are stuck with this, and that's not a pun on the fact that the particles are stuck. It's just that we've also tried a vibrating landscape for which we did an experiment, theorist experiment, where we were able to see these structures, but given our background, so much that we could do. No, the particles interact. Here, there's purely elastic collisions. And here they interact through a soft potential, standard jamming potential of V of R going as 1 minus R over sigma squared. Yeah. But the point of this is just to illustrate the fact that these particles don't distribute homogeneously. That's just the take-home message. And, there are experimental sort of evidence going back before us, which shows that if you put finite-sized particles in a flow, they preferentially concentrate. All right? As soon as they have a finite size, a density different from the flow, they tend to clutter. All right? And that's sort of controlled as by the so-called Stokes number. So, so there are ways to quantify this preferential concentration in flows. And this goes back to ideas which have to do with ideas of G of R in sort of liquid state theory, etc. But the way people in our community do it, for whatever odd reason, is to measure the probability of pairs of particles within a distance r, right? And you say this scales as r to the power d2. d2 is the correlation dimension. I mean, you understand why we do it, because we are after fractal structures. So the choice of words, choice of terms such as correlation dimension, etc. And then you measure d2 as a function of the Stokes number. Stokes number is just a shorthand for saying how big the particles are. So when Stokes is 0, that's essentially traces, then d2 is equal to 3. It's equal to the spatial dimension of the flow. The flow samples all of phase space, particles which are traces sample all of phase space, and so d2 is 3. However, for finite Stokes, it really goes down very small, and it's about 2.2, etc. And then when Stokes becomes very large, and again, I'm not going to go through the full theory, but as you can imagine, Stokes number large means the particle response time is diverging, so it really doesn't care about the underlying flow, and hence it again starts filling up the whole space, all right? So this non-monotonic behavior is something that I'll come back to at the end for non-spherical particles. Right? So this is, again, still, I'm sort of summarizing Rama's talk. I mean, I was there, so I actually went through it on YouTube once more to sort of see how best to summarize what she has been saying. All right? Okay. So, again, within the spherical particle, because that has a slightly longer history of 20-odd years, non-spherical has a shorter history, if you will, in our community. The typical questions that people have been asking, especially with a view to clouds, with a view to volcanoes, with a view to engines, are questions of the sort of how fast do droplets settle under gravity? Can we come up with predictions, theoretically otherwise? How fast do droplets hit each other? How fast do droplets coalesce to form large aggregates? And the sort of hope in all of this is that much of the physics, because we start with the Navier-Stokes equations and the sort of Maxi-Riley type equations, the hope is that most of these sort of plots or predictions would hold whether you're talking about a warm cloud or whether you're talking about planetesimals, embryonic planets giving rise to... the hope is that the physics and these sort of questions and predictions are sort of universal. I'd just like to point out just one thing, which is, I mean, I don't know how far it's visible, but this is just a principle of proof kind of plot, is that, for example, here, there are dots and there are lines. And luckily, it's not very visible, so I can go ahead and make the following claim, that the dots and lines are reasonably coincident on each other. The dots come from experiments in Eberhard's group. The line comes from theory and simulations done by us, just to say that the equations now have a reasonable footing, however simple they might look. Okay, with that sort of preamble, which covers the earlier talks on turbulent transport in about 20 minutes, let me come to what I'm going to talk about today. So that's all spherical particles, where, you know, exciting work is going on in many places in the world, including here at ICTS. I mean, Priyanka Mohit's sitting there, they're working on these problems. Now, what happens when you put more degrees of freedom in your problem, all right? So I'm going to list certain examples, again, just to have our ideas fixed, is, for example, you can think about deformable large droplets, all right? So in everything we said, our particles are not deforming, right? However, if you have an emulsion, for example, then these drops tend to stretch or deform, and one's interested in, for example, the dispersion, the breakup statistics. That's one example I which is going beyond the spherical model, and here's a cartoon of how these drops. Yeah. I'm not going to tell you about this because it's a slightly older work, so I'm not going to comment, but this is something that we had done only, since you asked, a work in 2014, I think, where we had looked, it's quite old, so where we had looked at if you just had hard spheres which are elastically colliding, and then in the asymptotics of small Stokes number, there's an analytical way to renormalize these Stokes number under these events, okay? But even then, you are sort of limited by how large it can go. So technically speaking, these theories are valid when the particles are smaller than the characteristic fluid length scales, the Kolmogorov scale. But now I'm talking about things which can really stretch, okay? Yeah. Yeah. But we can talk about what that renormalization factor is. Yeah, that's what I'm going to do, okay? So then one can also look at models such as this. This is the sort of simplest extension, what we would like to call, think of as flexible macromolecules. Essentially, you take three beads, you stick two rods, you have a stiffness potential, you have a bending potential, and you want to study what their configurations are. Again, for simpler flows, such as a shear flow, or what's known as a Batchelor-Crichton flow, or a smooth random flow, there's a lot that you can do about the marginal distributions of these angles. And the approach that we have is then calculate those, then put them in a turbulent flow, and fingers crossed, the results from turbulence turns out to be very different, so we can still ask for computational time and run simulations to show that they're different. Or we can also think about spheroids and ellipsoids, right? So these will have a sort of rotational degree of freedom, and then one can sort of ask questions which have to do with what are the sort of orientational statistics, what are sedimentations. For example, in JNC, Ganesh's group, we are looking at the sedimenting torque when you have these ellipsoids which have finite inertia. And finally, you know, not finally for my talk, then one can look at what we call elastic chains, which are a sort of prototype of a fiber, of a polymer, of a filament, we don't know what. I mean, we do know roughly, but this is a very generic model where, again, you have another degree of freedom. These are extended objects, and the whole idea is, for example, to see how different they are from just spherical small particles, all right? No, these are fixed. That's allowed to change shape, yeah. So this, I actually don't know how to squeeze them any further. So I can tell you where these ideas stem from. These ideas actually stem from, if you go from warm clouds to cold clouds, ice crystals in those clouds seem to have exactly this sort of shape. So that's why with Ganesh, we are interested in how these guys sediment and stuff. Yeah, so this polymer is a bit of a squeeze. I'll come to that caveat later, but I can tell you. These guys will stretch all the way to inertial range, so they won't really be polymers, because polymers will be controlled by the cutoff length scale. Yes, yes. So that's one of the references, I think, which has to do with elastic turbulence. So those we've sort of looked at with Dario, where even in a dynamical system such as the shell model last year, we showed how the Lyapunov exponent, the onset of elastic turbulence, begins at small enough Weisenberg number and Reynolds number order 1. Yeah, but I'm not going to discuss the concentration effect. Yeah. And no, no, we aren't looking at them sort of folding and forming yarns around themselves. Yeah, that's right. And I'll tell you one of the reasons why we felt that was a good starting point. Yes. No, and also the fact that there were these bunch of papers with by Steinberg and others, which were experiments for extended objects such as this. And luckily for us, they did not see in their experiments, things were just stretched out and were never. You mean in a real system? No. So of course they won't be elastic. So even in problems such as this. Yes, so that's the best we can do right now. For the cases where the particles actually deform, and Mohit's working a bit on that, and we are sort of getting somewhere, I hope. There we are sort of stuck more numerically in terms of resolving all the events, etc. The elastic collisions actually came about because we, again, this is a digression, but I suppose it's okay with the nature of the meeting. So the idea, which is not listed here, but the idea of elastic collisions came about because when we were looking at these equations, we found that there was an analog of an inelastic collapse purely through elastic collisions, but because the dissipation was happening of the flow particle coupling. And so we were able to sort of, just take the sort of simplest equation you can and do an asymptotics for the small Stokes. And what we were able to see was that in a finite time, you had an exponential number of collisions. I mean, the physics is rather simple. I can just explain this. I mean, the maths is a bit more complicated, but phenomena that's happening is the following. For small Stokes, that's the particle relaxation time is small compared to the typical flow time scale, turbulent or otherwise, is when you have two guys coming and hitting each other. Now they collide elastically, so they preserve momentum, etc., and they go back. But because the response time scale is small and the flow hasn't changed its configuration, they come back, and they come back. And then they form aggregates, which, ambitiously in that paper we had called a sticky event, where they sort of form these long-lived aggregates in the small Stokes limit. So our motivation was looking at it there, and then when we sort of put in hydrodynamic interactions, because for the simple system it's easy to do, we found that the effective Stokes with short-range hydrodynamic interactions tend to get renormalized to something else. I had spoken about this to you many years ago when we were doing this work. I just come back. Yeah, okay. So, okay, so I will sort of, for the rest of this talk, I will sort of talk about these two systems, all right? Because this becomes too technical. As you can see, it's a JFM paper, so it has lots of matrices, which I don't think is a good idea to throw at you. So I'm going to talk about these two systems and see where we go. Okay, so let's talk about chains and fibers. The preamble, we all, I think I can sort of go about this, except to say that experimentally nowadays we have excellent Lagrangian measurements which can track small particles in a flow. And the effect of inertia, as I sort of argued, as Rama gave in a talk, has been well studied. The question that we are asking is, what about other internal degrees of freedom? And the simplest extended object that we could think of was a chain which has n beads. So if it's 2 beads, it's a dumbbell. And you have these phantom links. And I'll tell you a little bit about how these links are constructed. and these are released in the flow, 2D or 3D. All right? So what they have is, in the absence of these links, each of these beads are like traces. They would sample the flow homogeneously and uniformly. Now you have an elastic coupling between the nearest neighbors with two free ends, and we'd like to see what's the dynamics of this object. Okay? Are you asking me, or as far as we could tell, no, actually. The reason is the following: that people who have looked at elastic chains are essentially coming from your sort of world, and what they do in flows, especially not the polymer case where things are small, and I'll make that distinction later, but for things which stretch in technical language up to the inertial range. People are just not interested. I mean, it's a model which doesn't come naturally if you're doing fluid mechanics, right? Yeah, but polymers are short, are smaller. Need not be, but in flows, for example, the studied case, both experimentally and otherwise, are polymers which are really small, which sort of we've looked at in other contexts. As Chandan was saying, we had worked on this elastic turbulence issue where you look at concentration and how you see how things kick in, but not extended objects. As far as we could see, there was none. Yeah. So I'll talk about that. So that's the standard Fenny model, which reduces to, for example, the Rouse model in the case where again, Srikanth, your question, where the intermediate separation is so small that you can get away approximating the velocity difference across beads through gradients. Now, if they're large, you can't work with just the gradient of the field, which in case of laminar, for example, is just constant sigma. So that's the sort of complexity in this issue. Okay, so it's a good point to sort of cover myself and say that this is really a toy model, and so far from fibers. Okay, so that's the archive reference. It's under review in PRL right now. Okay, so what is the simple description of our elastic chain? And this is the following. So I've just taken two just for simplicity, but we can build up this chain as much as we want. So first, of course, we need to derive an equation of motion for the center of mass. So there's the thermal noise, which is acting on this chap. And you have this, Chandan, what you were asking, you have this maximal separation. It's really the Fenny model. For people who are familiar, the only change is that in standard polymer physics, if you read Bird's book, etc., what you will have is not the velocity differences, but typically you work with velocity gradients because you're looking at small extensions and flows are smooth in the absence of any proof on the Euler-Navier-Stokes equation at those scales, so you can get away with gradients. However, when we would like our chains to extend all the way, in which case you can't do that because the turbulent velocity field has a certain roughness. It's not really smooth at those scales. There's a 1/3 Hölder exponent, so one has to work with velocity difference. So this is the sort of equation of motion for each of these links. So you just put in the drag force of the fluid, you put in the elastic coupling, you put in the noise, and this is the equation of motion for the center of mass of this guy. And the ratio of elastic to flow time scales, again borrowing from polymer physics, we call it the Weissenberg number, which is just going to be the chain relaxation to the fluid relaxation time. So I'm going to sort of present you results from 2D calculations because that's most dramatic and convincing, as it was also for preferential concentration, but I'll sort of discuss what happens in 3D. Okay, so here's a snapshot of This is a snapshot of the center of mass. I guess you can still sort of make out that there are black dots which seem to be sampling the flow reasonably uniformly. This is for small Weissenberg numbers. If Weissenberg number was exactly 0, they would be really homogeneously distributed. For finite Weissenberg number, you see something strange. You see there's a proliferation, there's a heavy concentration of these black dots in vertical regions. Now, this is a very strange phenomena, because what do we have? We have a bunch of tracers which are supposed to sample a flow uniformly. Just connect them with phantom links, which have an elastic coupling, and lo and behold, it starts to sample a flow completely selectively. And what's worse or more interesting is, just going back to our spherical particles, if these were particles, then they would all sort of live outside these vortices, because vortices would act as a centrifuge and kick them out. Whereas here, they all get sort of trapped in vortical structures. So if one worries about the elongation of these particles, so here maybe I should start again. So the top panel is for small Weisenberg number, the lower panel for large Weisenberg numbers. They have a finite length, which Chandan we took to be reasonably large to sample all of flow structure. So if you see for the small Weisenberg cases, these chains are stretched out. Initially, if you had noticed, they were really small, something like this, between my two fingers. As the flow evolves, they get stretched out. And for the large Weisenberg number case, they really get stretched out into lines and are pinned to these vortices. And I'll try to, yeah. Yeah. They're essentially, yes. Exactly, and then you get folded up there. But not in that yarn-like that we are discussing. Yeah, exactly. And we'll see, quantify this behavior in a bit. But I just want visually the phenomena. This is a really strange phenomena that, this competition between an elastic coupling and what a flow does to a tracer. I mean, it's just that. And that gives rise to this sort of, yeah. This is for the follow-up, we'll keep this in mind, or at least Jason, who's not here, should keep this in mind. Yeah. That is really the guy which is stretched out. Yeah. Yeah, but opposite sort of signs. So, yeah, I didn't show the color code, yeah. I mean, typically in 2D, you come in pairs, and because of entropy conservation. So if you began with something which I mean. Okay, so these are really like broomsticks for large Weisenberg. So as you preempted what I'm about to say, is that one can sort of look at a quantitative measure of this preferential sampling. And in 2D, what we look at is what's known as the Okubo-Wise parameter, which which is really comes from the fluid gradient tensor, and a working definition would be a scalar number, which is the difference between omega squared and sigma. Sigma is the strain, the amplitude strain tensor, if you like. And this sort of tells you lambda positive or negative. It's a point measurement, right? You can go to each point in the flow and measure what its lambda is. And this chap will tell you whether that point is a vortical or a straining region. Okay, so my colleague, for example, Prasad at TCIS has worked a lot on these things during his some years ago. All right, so what we did was we made a Lagrangian measurement of the mean lambda. All right, so this is the lambda sampled by each of these chains as it goes in the flow. So it's a Lagrangian measurement, all right? And if you look at its PDF, so the lowest ones are the standard sort of tracer zero Weisenberg case. I mean, this is a well-known picture. But as Weisenberg number increases, you see a preferential sampling of positive lambda. Similarly, you can look at the stretching, and that was your point, and you sort of look at the fact that whether as you increase Weisenberg number, do you see stretching behavior. But what's more interesting is this question of universality. So let me explain this a little, because this is a rather interesting non-monotonic curve, and hence possibly interesting. So I can build my fiber or my chain in different ways. I can take a piece of, take this example with lots of salt. I can take a piece of rope. I can make the maximal length a constant L, and then I can have many links. So I can put in 10 beads, 20 beads, 2 beads. So what's really changing is my interbead separation, right? So I'm looking at the mean lambda, which is sampled by a chain, function of the Weisenberg number. What are the different colors? The different colors has to do with take the same material, but put in more links or less links. Essentially, all you're changing is the inter-bead separation at equilibrium. Or number, yeah, exactly, number of couplings, or at equilibrium, whatever the... No. Because, exactly, and that's what we are, that's what exactly this plot will tell you. So we've looked at, I mean, the next slide will show you a little bit about what happens when you work with the spring, with the kappa in the coupling case. But what we see is so you have more bending, you have more bendings. Yeah, you have more bendings, basically. So what's going on is the following. The relevant length scale in the problem is really the ratio of the length scale of the fluid and the inter-bond link. All right? So remember that D2 curve that I showed, which had this non-monotonic behavior. It has a minima at a finite particle size, and then it goes up. This is something very similar, right? So the mean lambda for cases where the number of links, so LF is the fluid length scale, let's say the vertical length scale, or this could be the length scale of energy injection, so the forcing length scale. I think that's the best way to keep this in mind. LM is the maximum length of the chain. I keep that a constant. I just change the number of links by changing the number of beads. All right? So as I increase, this chap, then the mean lambda saturates as Weisenberg number becomes larger and larger. However, when ratio starts becoming reasonably finite, that means when the number of links has dropped, the number of beads has dropped, so you're getting more and more like a dumbbell, let's say, or a trumbull, then although there's a sharp maxima, it quickly goes back to uniform sampling. So even when the Weisenberg number is large and there's a strong elastic time scale with respect to the flow time scale, the fact that your interbead separation just doesn't have the freedom with respect to the forcing time, with respect to the length scale of the flow, makes sure that it just sort of peaks at Weisenberg number 1, where the two time scales are comparable to each other, and then again it forgets all about its elasticity and starts behaving like a tracer. So this non-monotonic behavior was rather interesting. Okay, there's still a question mark on the universal. There are sort of there are some other sort of calculations that some of us are doing just to understand this. But again, just to get a question, Hatami. Yeah, yeah. No, these are all tracers. Yeah. So there is no 3 here. Oh, this is reasonably accidental, actually. This 3 is sorry. Yeah, this is. I didn't notice this. Thanks. I should keep this in mind. No, what's happening is there is no Stokes number here because each of these beads are tracers. So it's Stokes 0. So so the only control parameter here is the elasticity time scale and the flow time scale. All right. So now if I have chains where the inter-bead separation is of the order of the sort of forcing scale in the flow, etc., then the behavior leads to a saturation. If, on the other hand, that separation is much larger, so it's not really sampling the small scales in the flow anymore, because the interbead, it can get stretched out, it's never coming back and sort of getting pinned to these vortices. That's all it's sort of saying. The analogy I was doing was the fact that hard spheres also don't preferentially sample the flow. I mean, that D2, but that's about it. But the mechanisms are very different in terms of, I mean, this is really arising because of this added degree of freedom that we gave for these phantom links to sort of squeeze and stretch. Okay? So, similar plot, I won't go through this because I have about 15 minutes left, so I want to move to other stuff. But we had sort of looked at, we are now looking at the case where, so just to say that in 3D, turbulence, the effect is the same. You see the same preferential sampling. It's not so dramatic because when a chain gets trapped in a three-dimensional vortex filament, there is vortex stretching in 3D, right? Unlike in 2D. So what happens is that it can stretch out these filaments much larger, and hence if you make the same sort of measurement of how preferentially sampling the flow, I mean, the effect is not that dramatic, and you really need larger and larger Reynolds number to make the vortex code in 3D to be strong, and as Mohit and Priyanka will complain, it's impossibly hard to do larger and larger Reynolds number simulations. So, I mean, I'm always happy with smaller Reynolds simulations. Yeah, but then the vortices break, actually. So if you want, I can show you some of this very nice stuff on at my laptop. And now we're sort of looking at just this thing, so we would like to see the role of inertia, because it's a competing effect. Inertia will drive it away from the vortex. The elastic coupling will try to pull it back. So where are these chaps pinned? And also it seems that there might be certain sort of biological interest to look at these filaments if you have inertia in them. You know, these things which shoot out in case of spiders, etc. I mean, we're sort of looking at some of that literature just to find a context to these fibers beyond beyond the fact that, you know, one hears about harmonic chains a lot, not in turbulence, but in other fields. Okay, and we'd like to sort of certainly see how do they settle under gravity, because for spherical particles, we know the answer, as I was saying some time back, but here things are pinned to vortices. So are there sort of preferential settling under gravity the minute you make these beads heavy? You know, you put a little mass and you know, active filaments probably at some point. Okay, so in the Bulbul, can I sort of continue for 10 minutes? Okay. Oh, sorry, Chandan, you were sharing. Sorry. Yeah. Okay. Yeah, I'm just worried unless it becomes too much of a strain, especially for the students. Yeah. 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 Yeah, in the drag reduction scenario, what happens is you have the coil stretch transition, right? But those are all small scales. So we sort of avoided that by, so at small scales within the coil stretch transition, the polymer sort of sucks out energy from the flow. So I mean, Rahul has worked a lot on these problems, Rahul Prasad, etc., where you do see, for example, the energy spectrum as well changing its shape at large K. Yeah, but those are all small scale phenomena. So what we wanted was a chain which should ideally explore the structure of a turbulent flow, and hence we wanted it large. That small scale things are smooth. So, I mean, again, modulo any theorems coming in as of today afternoon, as far as we know, solutions to Navier-Stokes psychic equations are smooth at small scales. I mean, in 2D, that's the theorem, sorry. In 3D, we do not know in terms of singularities, etc. Yeah, so those pictures sort of are valid when when in penny P, the P stands for this approximation, the Petelin approximations. So in cases where the Fenny model are used, where the maximum length is governed by the Kolmogorov or any cutoff length scale, then all these phenomena of drag reduction. And the other point, of course, for elastic turbulence, it's a similar exchange between, so even in dynamical systems such as shell models, if you modify Fenny P type equations and then you set your flow to have basically order 1 Reynolds number, right? And then you increase the concentration of the polymers, you can see for a finite Weisenberg number order 1, there's sudden transition to a chaotic regime, the elastic. I think Rituborn and you were also looking at this? Yeah. And then as you increase concentration, you do see that the level of chaos sort of starts increasing. Okay. So from chains to particles which are also extended, but now these are rigid particles which could either be oblates or prolates. I keep getting lost which one is called which. So they could either be disc-like or rod-like. I mean, that I tend to remember better. And they're sort of given by an orientation vector P, which sort of tells you which way it's looking. All right? So, cookies are oblates. Okay, I'll try to remember. Oh, I see. Okay, this I did not know. A spindle. Never like to remember this. So which is why in the abstract I just called it rods and distance so that I don't make a mistake with this. And also I think there's a strictness about whether you're really talking about ellipsoids or spheres, in the sense whether you have two symmetry axes or one symmetry axis. So in all fairness, I'm talking about spheroids. So there are A not equal to B equal to C kind of systems. Okay, so again, there's a lot of, there is some work that a bunch of us are doing on these non-spherical particles, which really have to do with how they sample flow structures and what flow does to it. I mean, the main question, I think, this is my point of view, is how do sort of crystalline structures in clouds in colder climes sort of tend to settle, why they orient the way they do, and that has implications on the microphysics there. But I'm sort of not going to discuss that because that sort of gets too turbulent, but again, keeping in mind the name of this program, I'll sort of talk to you about something which I know very little, but I think it's fun, so I'll just take the risk and sort of discuss that, which is these objects that we sort of use them as model microorganisms, micro-swimmers, to sort of understand anything about collective behavior. I mean, in Bangalore, being in Bangalore especially, we hear many talks on collective behavior. And as you remember from my second slide, there was a picture of a plankton. I've been showing this picture forever since my job talk days. And so I decided at some point one should actually do something about it. So there's a very bright undergrad student from ISC, actually, Amal Roy, who was here for his master's program, master's thesis, and he essentially worked on this with me. We had a backup thing so that he did get a PhD position, which he did, which was on things which are more standard, which had to do with orientational statistics and distributions. Okay, so what is the idea? So the idea is, can we extend the Wick-Zec model, because that's the simplest, for particles in a flow? So certainly to this audience, not to a turbulence audience, to this audience, I don't need to sort of highlight what was done in this paper, but for the students, just a quick recap. You take a bunch of self-propelled active particles, no flow, that's where I believe we'd like to come in, and you allow them to move, and you say that these chaps can see within a certain, up to a certain distance. They're not very myopic, so they can see a little further away, chemically or otherwise. And at discrete time intervals, they would tend to reorient themselves with the average direction of all the agents within that radius. Okay, that's the rough summary of this model. And then when you sort of measure in different ways the average orientation of this bunch of active particles, you see that for certain conditions, certain noise, etc., and there's tons of work on this, and I'm not really the expert to talk about it. You see that there's an average alignment of these chaps moving there. So some of us who've sort of been working on turbulence, turbulent transport, etc. for a while, I mean, just a few of us, we've been sort of wondering what happens if there's a particle-fluid interaction, all right? How far does this picture change? Because the nice thing is, the flow is turbulent, there are vortices which will expel stuff, so flocks should break up. Yet, there are measurements in biology sort of journals, which I can't pronounce very well. I'll show them to you later in the next slide or so, where there is enough evidence to show that micro-swimmers, which are reasonably, swimming reasonably slowly on slow time scales, do tend to show rather strong collective behavior. So I'll begin by sort of at least two attempts that I'm aware of, were by Nick's group, which looked at stability of model flux in a turbulent light flow. So what Nick did was, he's at Yale. What Nick did was just to say that this was Vic-Sec with up to the term Vp delta t, and then he added this perturbation which is coming from the fluid, right? But his fluid velocity is really a model solution, not a solution of Navier-Stokes. So if I remember well, it was constructed from Ornstein-Uhlenbeck-like systems with a finite correlation time, etc. And then, you look at his flock, and they do seem to flock, all right? And then there was another work by Bagley a year or so ago, which had to do with steady flocks in vertical flows. So again, these are model flows where you have solid body rotation, so you just generate a vortex and you try to see how these active agents can circumvent these vortices. Okay, so that's the background. I'll talk a little bit about at the end what where all this comes from. Okay. So what we were curious was what happens when carrier flow is complex, and beyond traces, what happens to find if you have particles with a finite size and shape? Are there sort of magic shapes and magic sizes which tend to flock? And if they do, can we be lucky? And I'm really using that word with all caution, and actually go back and check, do those size particles model swimmers actually flock or not? I mean, just as a proof of principle. All right, so this is sort of work that some of us have been doing. So the strategy is very simple, that we take small, finite-sized, self-propelled particles of shape with all sorts of shapes. I'll show you in a bit. And we would like to see the effect of flow, and etc. So again, the particles have 2 degrees of freedom. One is the rotational degree of freedom, which comes from the standard Jeffrey type equation, which tells you how fast your thing is spinning. And you see that the effect of both the straining and the vertical component of the flow comes into this. And you have the translational degree of freedom. This, again, is not as simple as the case of spherical particle, because this resistance tensor is time dependent, because at different times you are looking in different directions, so you have to simultaneously solve for the resistance tensor, all right? And then what we do is we cheat badly, which is we say that the effective velocity of the fluid, of the particle has a certain component which is self-propelled along its orientation vector, and a component which is influenced from equations such as this, so we all add up all the forces correctly. So it has essentially 2 components. One, which is it's self-propelled, it wants to go along its p vector, and the other, what the flow is doing. And after that, the sort of relations among the particles are exactly Vic-Sec-like. So we choose discrete time intervals, we choose discrete radii, etc., and we see what's going on. And the fluid, of course, is 3-dimensional Navier-Stokes. Okay, so this is a matter of detail. Let's not go into it. Just to say that there is information about the shape of the particle and the size of the particle, which goes into this drag term. All right, so it's all encoded, and the shape is also encoded in the Jeffrey equation. Okay, so I won't go through all of this, but just to say that in the passive limit, this was Amal Roy, who's a student undergrad at IIC, Amal's work, really, where he looked at all the orientational statistics, which were then confirmed with experiments from both Anderson's group, Odenchad's thing, and the Pumir-Wilkinson, just to say that the passive model that we have is all right. I mean, I'm not going to talk about this thing now. This graph is actually interesting. I mean, I'll just show it nevertheless for just curiosity. This is from the paper by Federico and collaborators, where they actually take a rod and they image it in time. And if you look at it closely, you'll see that how at certain these are passive rods. They just flip around and then they start again going like this. It's beautiful to look at, actually. So this is our starting point. Okay, so now for some animations in the 50 seconds I have on the clock there, is if you have no self-propelled velocity, I'll quantify these in a bit. So if there is no self-propelled velocity, it's just different shaped objects. I think the left panel is rods. Some of them are rods, some of them are discs. I mean, in this case, it actually doesn't matter. You see that they all move around, but they, visually there is no evidence of any emergence of collective behavior. Now, if I put in a little bit of self-propelled part and we vary this, then, for example, I think this one, if you look at this chap, you do see things. I'd love to say they look like the measurements in Rome, but the scale separation, I think, is of the order of 1,000 or something. But they do look as if there could be something where there is an emergence of an ordered behavior in a system which initially was completely random, all right? And sort of this we've looked at in various ways. So, I mean, it's very nice when, especially when they don't know what to do. There are points in this movie when there's a whole bunch of them which are unsure which way to go, and suddenly they break the sort of, I mean, I'm hesitant to use the word symmetry, but they break something and then they decide that they need to go all in that direction, okay? So, sorry, what's coming from the floor? Yes. Well, if you just have Vic-Feck-like behavior, I mean, if they're Vic-Feck minus the fluid, right? So then you have the standard results. Now, when you put in the flow, then the size starts becoming important, right? Without the flow, what is size? There is no evidence of size, right? It'll only depend on, for example, if you're worried about finite size effects in an ensemble, then you sort of think in terms of noise, you think in terms of radius of. What we are arguing is, if there's a fluid coupling, then not all of them will behave the same. You have to be a certain size, or you have to be a certain shape, or you have to have a certain velocity of, your activity should have a certain level, a narrow band, where this phenomena can emerge. Otherwise, you don't, and I'll just quantify, I think I should stop soon. Okay, so for example, when you look at the global order parameter, I mean, this is just one snapshot really, is, you can't read the numbers, but essentially there's a whole bunch of, so this is V0, the level of activity, this is the radius of interaction. There are snapshots, I mean, all these scales are not the same, right? I mean, here, even the green is order 10 minus 4 or something, so there's absolutely no order in certain regions of this plot. Whereas if you look at, okay, so I should say, in each plot, the x-axis is the Stokes number on log scale, the y-axis is the shape parameter, all right? And each of these represent one set of simulations for a given activity and a radius of interaction. So there are certain cases, for example, here, where you find nearly, the global order parameter is nearly 1. So you do see nearly complete ordering, even in a flow which is trying its best to break up that flock. Right? So, so again, I'm not going to discuss this now. We've also looked at the nematic order and the scalar sort of nematic order to see whether you do have evidence for nematic order in these flocks. And they're not completely one-to-one mapped with the global order parameter. I mean, they're much less robust to variation, but you do see a nematic order of around 0.7, 0.75, which is pretty large, I mean, as far as we could tell. So, a couple of years ago, this was again with another summer student who's now doing his PhD in the US, in Virginia, where he had looked at the same problem in 2D flows, but without any shape particle, just spherical cows. So spheres, but different Stokes number, and again, the same sort of picture emerged. So I think I'll just stop here, actually, because I'm over time. So just to conclude saying, I mean, this work that is going on now is under review right now. So just to say that we would like to look at, or we are looking at the role of external carrier flows in the collective motion of these microorganisms. And the fact that turbulence, for certain magic shapes and sizes can actually stabilize flocks. And this was quite interesting. We actually went and looked at these books, Hydrobiologia, etc., animal groups, and then we are able to come up with classes of zooplankton, which coincidentally, I should underline, had the same sort of Stokes number and the self-propelled velocity as a ratio of the fluid velocity as we did. And this was a chance coincidence. One shouldn't read too much into it, but that sort of gives us some of direction that it's, probably one can sort of play with these systems a little. And then we'd sort of like to look at various problems related to these models, even if as model flows, especially these are fun problems for summer students to sort of worry about. And just lastly, so there was this paper, I don't know, which was just a year or so ago, which sort of looked at in a suspension in the lab, which sort of saw the sort of correlations that we were seeing in the two-dimensional case, and that again seemed very hopeful for people like us. Okay, I've sort of gone badly over time, and I should really stop and take questions. Thank you.